If possible, simplify the limit as x tends to 1 of, so we got a function up here. It's not a function defined through a formula the way we might understand it. It's defined through an integration. But there's this little x here. The other bound is 1. And then we've got some expression in terms of just some other variable, some dummy variable. We use t. So that over x minus 1. Now, at first glance, a limit like this might look intimidating, but what should we usually do when we encounter limits? You should try to plug in and see what happens. Okay. Now, plugging in a 1 on the bottom, we'll get a 0. Okay. And one of the definite integral properties is that if both bounds are the same, right, just visualizing it, if you're trying to find the area under a curve, but you start and stop at A, well, there is no area. So you can see pretty quickly, okay, that's going to be 0 as well. Oh, so we have a 0 over 0 situation. Now you might say, well, okay, 0 over 0, we could probably simplify this. What could we do? Well, the problem with the integral up here is it's not going to allow us to, say, factor things. Okay? The integral is very much in the way in that top function. So how can we get rid of an integral? Well, differentiation. Differentiation with limits? Well, that's the sort of thing L'Hopital's rule does. L'Hopital's rule says, oh, you see a 0 over 0? Well, try taking the derivative of the top and the derivative of the bottom and seeing if it'll work out. Okay? So that's exactly what we're going to do. We're going to try L'Hopital's rule. So I got x minus 1 here, x going to 1, and then it was t cosine pi t dt. Just want to double check that that's right. Never want to do a question. Never want to answer the wrong question. Yeah, okay. I thought that pi was in there. Okay, so we're going to use L'Hopital's rule, so I'll use the usual L apostrophe H that I like to use to symbolize I'm L'Hopitaling. So it's still a limit as x tends to 1. Now, the derivative of the bottom is really nice. It's just going to be 1. So as long as the top works out, we should be able to answer this real quick. So how do we differentiate the top? Well, we're trying to take the derivative of an integral. The problem, however, is the derivative of an integral can be a little tricky sometimes. Okay? Now, the fundamental theorem of calculus part 1 says that if you want to, I'll write a version, this is not the only way it's written, but if you want to differentiate a function defined through an integral, as long as there is a constant, some a down here, and just a single instant of the variable that you're differentiating, so just an x by itself down here, then, and only then, does the derivative and the integral cancel out, and you're just left with the function inside, obviously with your dummy variable replaced with the variable of differentiation, in this case x. Well, oops, we don't have this. We have the x and the 1 are in the wrong spots. Now, we can go through sort of this a big sort of rewrite or workaround. That's definitely an option. In this case, we can actually do something nice using definite integral properties. Okay, if you're doing a definite integral, I'll just write it roughly. If you want to switch the bounds, you can do that. All you got to do is introduce a minus sign. So I want the fundamental theorem of calculus part 1 to apply. It won't. These guys won't cancel each other out, but you know what we can do? We can rewrite it in terms of something that will have the fundamental theorem of calculus apply. So usually I use square brackets. So we can write it as minus, and you get to switch the 1 and the x. This is one of our definite integral properties. I'm going to drop the divide by 1. We don't really need it. Now, when it comes to taking the derivative, that minus sign can come out. And then, what have we got? We've got the derivative of constant to the x with our integration. So those guys cancel. And we're looking at the limit as x tends to 1 of minus, don't forget your minus sign out here, and then whatever's inside, so x cos pi x. So now let's try and take the limit again. Well, this is continuous, that's continuous, so we could try and just plug in minus 1. Cosine pi times 1 is just cosine pi. Well, that's minus 1. So with minus 1 times minus 1, the answer to this is 1. This limit evaluates to just 1. We had to use the fundamental theorem of calculus part 1 as well as L'Hopital's rule. Yeah, we had a 0 over 0 and there are other techniques, but L'Hopital's rule is the one that would allow us to differentiate, and that's what got rid of this pesky integration symbol that we don't have a lot of options with when it comes to other limit techniques.